everybody, welcome back to another fun and exciting pre-calculus class. This class is going to be a little different today. Not going to do as much kind of on my computer as I normally do. I'll do a little bit more talking through your textbook, explaining some things, explaining some words that you're seeing there. So go ahead and open up your textbooks to page 197. That's where we left off in the last lesson, 197, if you will. And we plotted this this graph. We took and we made this parametric equation, and we used sine and we used cosine, and we went through and we kept changing our variable, which was the theta, and we used 0, 10, 20, 30, 40, and so on, and we made ourselves a little graph based on that. All right, well, go ahead and turn the page to 198. And it talks about this first paragraph. I'm not going to spend a whole lot of time on. I want you to come down here to this second paragraph, actually third paragraph. The parametric equation are sometimes simpler to develop and graph than the corresponding rectangular equations. So sometimes it's easier, rather than to go into rectangular, which is what we did in the last example, sometimes it's easier just to stay in the parametric form. Consider, for example, the two-dimensional graph used to depict the path of an electron within the electron cloud for the Schrödinger standing wave model of the atom. In this model, the orbit of the electron is represented by a sine wave traveling along the perimeter of a circle as shown. So what we're looking at here in 10G is here's the circle, okay? And here is the orbit of the electron. It's a sine wave that is traveling along the perimeter of the circle. Now, there's some oscillation to it. It's kind of going back and forth around it. It's not following the exact circle. So we have here a parametric equation. Now, in figure 10H, only the first quadrant is shown. So what we do here, so that was 10G, that's kind of showing the whole circle. What they do here is now they blow up the first quadrant. So over here, in the electron orbit little section right here, this is what they're showing you is the first quadrant. So you can be looking at this in your book, obviously, as I'm showing it to you on the screen, but here is a blow up of that first quadrant section of the circle, okay? So only the first quadrant portion of the orbit is showing. Several additional line segments have been included to assist and develop. So let's talk about those different line segments. What do they have here? They have formed a right triangle. And so what you have is basically them showing you some different things. So what is this first section? This first section going to point C, okay, is showing you where it touches, and this is your theta. So this is your one rotation on your theta. So your theta is your angle. So your angle, you rotate it up once. This is your x prime, y prime. What does x prime, y prime mean? Well, your x and y are here on the electron orbit. So if you see, the blue line is the electron orbit, right? And the E point is where your rotated theta right here, where this line touches the electron orbit. That's the XY point. The x prime, y prime point, and what x prime y prime means, and I think we've talked about this enough, it means that they're related to each other, right? They're different but related to each other. So this is the C point, okay? You also have, if you look carefully, you also have an x double prime, y double prime, okay? So that's in there too, because look, you have another angle, you have another box. What's going on here? Lots of different stuff. So let's kind of keep reading this and see what these other points are doing. For the parametric equation of the circle with the radius r. What's the radius r? The radius r is basically this circle, this r right here. So going from, again, the center point over here to the edge of the circle, that's always called a radius. So that's an r. What is your r in trigonometry? Your r is your hypotenuse, right? So here's your right triangle, okay, OA and to AC. OC is your R, that is your hypotenuse. Okay, so that's what you're looking at there. With any point C moves along the circle along the curve as theta varies. So in other words, as theta varies, the radius stays the same. The radius is a constant. As we move theta around, we continue to keep constant along the edge of the circle. Now, when we keep constant on the edge of the circle, notice what's going to be changing. So as we move this line right here, this E point's going to change, right? So right here, if we move it up just a little bit, the E point's going to get closer to the circle. At one point, if we move the theta all the way up around, maybe 80 degrees or something, the E point is going to be inside of the circle and significantly inside of the circle. As you can see, this is the furthest point. This E point, this XY coordinate, is the furthest that the electron travels outside of the circle. Okay, so the closest that the electron would get to the center point is up here, like I said, maybe around 80 degrees somewhere. But our focus is down here at the furthest away point. So when the sine wave is at its furthest point from the circle, that's the E point. These can be related to theta by basic trigonometry, as the cosine of theta is the x prime over the r. What's the x prime? The x prime is our C point, okay, right here. And so over the r, so in other words, what's the x, okay? The x is going to be your adjacent side, so that's adjacent over hypotenuse, and that's cosine. Okay, so that's right there. Cosine is adjacent over hypotenuse. And then the sine would be the opposite. So what's the opposite? That's our y prime over our r. So that's opposite over hypotenuse, and that gives us our sine. Giving parametric equations, x prime equals r times cosine theta, and y prime equals r times the sine of theta. We just kind of delineated that. In other words, we solved for x prime and we solved for y prime. Now consider the sine wave. Line CB and line OA are parallel, forming your angle ECB. Where's ECB? This one out here. E. Where's C? Right here. Where's B? Right there. Can't really blow this up just the way I've got it set up on my computer, but you should be able to see this in your book. You should be able to look closely to it, even magnify it if you need to see what's going on there. So the inside there's a little theta, and so it's like this little theta is the same as this big this theta over here. So in other words, the theta of this big line angle right here is the same as this theta. It's not theta prime, okay? So that stays theta. As theta varies, CE varies according to A times the sine of B theta, where A is the amplitude and B is the number of cycles to complete between the 0 degrees and the 360. What's 0 and 360? That's all the way around the circle, giving CE equals A times the sine of B theta. So the equations for your x double prime and your y double prime, okay, that's right here. These are these small ones right here up by theta. From basic trigonometry, in the small triangle CBE, right, this little triangle up here, CBE, is CE equals A times the sine of B theta. What's B theta? B theta is this theta out here, by the way. X prime equals A times the sine of B theta times the cosine of theta, and Y double prime equals A times sine of B theta times the sine of theta. All right, complicated, I know. Turn your page. Finally, notice that the abscissa and the ordinate. The abscissa is your x coordinate and your ordinate is your y coordinate. Okay, so usually we don't use abscissa and ordinate, we just say the x and the y, but sometimes the book likes to just kind of test out your knowledge there to make sure that you're paying attention. Of point E are made up of the x prime and the x double prime and the y prime plus the y double prime respectively, or x equals, so x, that's the abscissa. The abscissa equals x prime plus x double prime, and the same thing for the y points. Substituting from equations at the end of the last two paragraphs gives parametric equations for the electron path S. So here it's kind of all delineated out right here. Here is the actual parametric equations that we're using. X equals r times cosine of theta plus a times the sine of the b theta times the cosine of theta, and y equals r times sine of theta plus a times sine of the b theta times sine of theta. Okay. Right? Blown mind. To graph the curve representing the electron wave, let r equal 1. So the radius equals 1. Basically, we're using one radius. 1 is going to be our base standard there for our radius. And a equals 0.02 and b equals 3, corresponding to 3 cycles in one orbit. Let the parameter of theta vary between 0 and 360 at 15-degree intervals. So in other words, every 15 degrees, we're going to change our theta. So we're going to have to recalculate this equation every 15 degrees. And that's how many times it'll go onto our graph. And then complete the table of values. So basically, it said all of that stuff to say, okay, now plug this into this formula and it will give you the answer. Okay, so now we're going to go back over to my computer and we're going to go through at least a couple of these to show you how this works. Okay, from the information they gave us, here is our formula. X equals r times the cosine of theta plus the a times the sine of the b theta times the cosine of theta. All right, now they also gave us that our a is going to equal 0.2, our r is going to equal 1, and our b is going to equal 3. So what we want to do right now is we want to go ahead and substitute all of those things into this equation wherever they go. All right, so let's start here. X equals r1 times the cosine of theta. Our first theta was 0, because remember our chart that we're doing? Okay, go run back over here. So our chart here, our first theta is 0, okay? Then we'll have to do one for 15 and so on, but our first theta that we're going to do is 0. So we're going to do cosine of 0 plus our a, so 0.2, times our sine of b theta, so b is 3 times 0. That one's going to be easy for this first one, times the cosine of theta, or 0, sorry. All right, let me go ahead and move these over here. All right, so now we just want to go ahead and work this out. You can plug it into your calculator, do what you need to do right here, follow order of operation, those types of things. Okay, so it's important here to make sure that you remember order of operation and things like that. So let's go ahead and let's section this thing off using parentheses. So we're going to do this, and then we have a plus sign here, and then we have this is all one piece over here. So let's go ahead and just start solving this. 1 times the cosine of 0. So what is the cosine of 0? So cosine 0 equals 1. 1 times 1 is 1. Plus whatever we get over here. So 0.2 times the sine of 3 times 0. So that would be times the sine of 0. So we need to figure out what is the sine of 0. Maybe you remember the sine of 0 is 0. So check this out. What happens here, as soon as that 0 is out, look, 0.2 times 0 is 0. And then the cosine of that, that's 1. But 1 times, anything times 0 is 0. So that zeroes out. So we have 1 plus 0 equals 1. So our answer should be 1. So let's jump back over here to the book. And let's take a look there. There we go. When we used 0, we got 1. Same thing is going to happen when we solve that for the x, for the y. I'm not going to plug into the y just for time's sake. But I am going to go back and do the 15 degrees. So let's go back over to our computer and let's kind of back up the truck here just a little bit. and let's plug all this stuff in, except for now, we are going to, everywhere that there was a 0 degrees, we are going to plug in a 15 degree. Okay, so cosine of 15, 3 times 15, and here again, cosine of 15. Now, let's go ahead and put those parentheses back on just so we remember that this plus sign is here and we don't kind of do things out of order. So the first thing that we're going to want to do is, and I just, these things all stay the same. Those are all constants. They don't change. So whatever they told us these parameters are, those are staying the same throughout. All right, so the first thing that we want to do is the cosine of 15. Cosine 15 equals, well, that didn't help us very much. There we go. We'll do them in decimals. So we get 0.965, 0.97, we'll call that. So 1 times that is just going to be 0.97. So 0.97 plus this right here. Let's go ahead and do this. I'll just do these separately. So we'll do the sine of 45. So the sine of 45 equals 0.71. So 0.71, and that's going to be 0.2 times that, times the cosine of 15, which we already did over here, 0.97. And then we can go ahead and multiply all those together and see what we get. So we have 0.2 times 0.71 times 0.97. And that's going to equal 0.13. I'll just leave that there. I won't round that off. And then we're going to add 0.97 to that. So plus 0.97 equals 1.10. So 1.1. 1.1. And that's x equals, right? So x equals 1.1. Let's go back to the book and let's verify that we indeed did get the correct answer. So there we are again. This time we did the 15, we did it for x, and we got 1.1. We did get the correct answer. Now, if you're doing this and these are going to take a long time, just FYI, sorry about that, right? But they will take a long time for you to create that whole chart and go all the way out, but you have to do the whole thing. You would also be using the y value. Where's the y value formula? It's right here. It's different than the x value formula. So you got to do it twice, and you got to do it a bunch of times. Now, typically, they're going to be a little bit kinder to you in the problem, and in the practice problems or on the test. They're not going to make you delineate the whole thing. They might say between 0 and 90 at 15-degree increments, something like that. So you would just have to do like a certain number of them. Couple of different things here at the bottom of the page on 199 real quick before we end. Just these are like famous math problems, I think is why the book kind of shows them to you. The involute of a circle and the cycloid. The involute of a circle is formed from a string wrapped around the circle. So in other words, you wrap this string around the circle and you like pull it around it, and that creates the involute of a circle. There's your formula for it right down there. Again, those are parametric equations. Now, this one's kind of interesting because I think probably if you've ridden a bike very much, whoops, sorry, there it is. There's the formula down there. If you've ridden a bike very much, the cycloid is interesting because maybe you've had like a clunk in your tire. You've had like a stick or a rock stuck into your tire. So every time you do another revolution, you clunk again. So spin your tire again, clunk, spin your tire again, clunk. So how many times is it clunking, right? So look at this. The cycloid is the idea of the wheel of the tire every time it makes a revolution, every time it touches the ground back in that same place. So right here, clunk, your stone hits the ground. Again here, clunk, the stone hits the ground because your bicycle tire is revolving around every time. And then here again, clunk. And so how do you form that graph? Well, that graph is formed right here. Here is the formula that you would use. And you would do the same process with the changing of the theta. And that would give you your other values for your variables. Okay? In this instant, the curve is called a brachistochrone. What is a brachistochrone? You need to do some research on that. You might be surprised what you find. It's a very, very famous math problem, but these are like concepts that are covered by that. The book kind of leaves you hanging right there, and I'm going to leave you hanging too because I want to see you do some more research. And you message me. You tell me what the brachistochrone is. That's all I have for you in this lesson. I hope you learned something there. Maybe you piqued your interest. Maybe you want to do a little more research and figure out what that is. Some of you are like, no, are you kidding me? I don't care what that is. All right, well, work hard. Do some of these practice problems. It is going to take you some time. You're going to have to fill out that whole chart. But look what the problem is asking for. It's not that bad. Once you kind of just start plugging into your calculator, you should be able to get these problems correct. If you wonder, maybe you get stuck, go back, rewind that video, watch how I did it, and plug in, and you should be able to get some answers there. Okay, that's all I got for you. Have a good one. Bye-bye.